Simple harmonic motion. What in the crap does that even mean? Well, it simply means something that oscillates. And that is a fancy word for saying something that repeats its motion over and over and over again. So something like a pendulum swinging back and forth. Like this. If we have a pendulum that we pull back and we let it go, it's going to swing out in an arch like this, and it's going to come to a stop on the other side, and then it's going to turn back around and come back this way. And in a perfect world, if there was no friction in the rope or the hinge where it's tied to the ceiling or any wind resistance, it would keep doing this back and forth forever and ever. Here we have a mass hanging on a spring, and right now, when it's at this point, it is at equilibrium, which means it is at the center point of all of the motion. And what we can do, we can pull it down, or we can push it up a little bit, and if we let it go, it's going to go swinging back and forth, back and forth, back and forth forever. We have yet another example. We have something going in uniform circular motion. So this is something we studied before, things that are going in circles. And if we plotted the position of the ball right there, if we plotted the position of that ball right there as time went on, then we would find that it would also follow simple harmonic motion. Because eventually, it keeps coming back to this point. So it keeps going in the same circle, and then it starts again in the same point, and then it goes into another circle. Here is another example, and this is a spring, but it's sideways, so it's sitting on a table. And for this, we're going to say that it's a frictionless table, so it never slows down. And this is our equilibrium point, x equals 0. So this is the point in the middle of the motion. And I can pull it to the left of a distance, let's say 1 centimeter to the left, so I'll say negative 1 centimeter, and I'm going to let it go. And when I let it go, it's going to get pushed to the right because we've got a force acting on this spring right here. There's a force there. And you remember that is, here we go, that force is the spring constant times the distance. So the distance would be 1 centimeter. So it has a force pushing on the block to the right. And that means when I let go, there has to be an unbalanced force, so it's going to go moving to the right. And it's going to go all the way to the right until it gets to positive 1 centimeter. And then at this point, we still have a force, but now that force is pulling it that way. So at this point, it's going to go back to the left. And it's going to keep doing this forever and ever and ever. It's going to keep bouncing back and forth. This is a guitar. And, in case you couldn't tell by my drawing, that is a guitar. And you know that guitars make sound. Well, sound is also simple harmonic motion because sound waves are just air particles and they are oscillating back and forth. And that's what you interpret as a sound in your eardrums. So if I pluck a string, it's going to vibrate and it's going to resonate in the guitar itself, and that's going to produce a sound wave. And all of those things are simple harmonic motion. They are all examples of harmonic motion because the motion of whatever it is, whether it's the string, whether it's the guitar itself vibrating, they're all moving back and forth rapidly over and over and over again. And here is where we start finding out how the math works. Now, this is going to be a graph, and we're going to plot the extreme points of something in simple harmonic motion. So when we are at 0, so this arrow right there, this arrow right there, we're pointing at this dot that's right on 0, 0. And that's at the very beginning. That's at equilibrium. And if I set it into simple harmonic motion, then let's say it goes positive the first time, and it's going to go all the way to some highest point, and then it's going to turn back around. Then it's going to travel straight back through the equilibrium point, but in the other direction. And then it's going to go to the opposite extreme on the other side. And once it gets there, it's going to go straight back to the center again. And you could probably see that this is a sine wave. And this is how we explain simple harmonic motion. So at any moment in time, we can tell, we can see where the object is based on the equation for a sine wave. So we have a sine wave here. But more commonly, it is actually, excuse me, more commonly what we'll do is we'll start the time once we either pull back the string or push the spring, and then we let it go. So I'm going to pull it away from the equilibrium point, and then I'm going to start my timer as soon as I let go. So I pull it, let's say I pull it to the right, or positive direction, and then I let go, and at one point it's going to go back through the center at the equilibrium, and it's going to go all the way to the other end. And then we know that it's going to come back around, and it's going to go all the way back to where it started and repeat the motion. And so that would be a cosine wave. Both can describe simple harmonic motion. Both can do it. There's no reason why you have to use one or the other, but more commonly we use the cosine wave. So let's just do a sine wave example, then we'll do a cosine wave example. So sine wave example is it's going to go from 0 to some amplitude A, back down to 0, back down to negative A, and then back to 0 again. So it's going to go up and then through the middle and back down to the bottom and then through the middle again. So you already know the equation for that line is some amplitude A times the sine of something. It's going to be the sine of something. And these points here, where I drew the dotted lines, those are very specific points in terms of radians of a circle. So when we go from 0 to the highest point, that's going to be pi over 2. When we go back through the middle, that's going to be pi. When we go all the way to the bottom, that's going to be 3 pi over 2, and then back to 2 pi again. So 2 pi would be one complete oscillation. It could be one rotation in a circle. It could be one motion between the two extremities. So if I pull it back and let it go and it comes back and lands in my hand, that's one complete motion. So that's 2 pi radians. So it's going to go at some angular velocity. Yes, that's omega. Going to go some angular velocity times the time. And that will give us our position. So this right here, let's do... Oh, never mind. Okay, let me just erase this here. So it was A times the sine. But more commonly, when you do an experiment, you can't really just set it into motion from 0. It's easier to pull it back and then let it go. So it makes more sense if we use the cosine instead. So here is our equation for the position of some object in simple harmonic motion. Alright, so here's our equilibrium point, and that's where we're going to say y is 0. Let me write that over here. So then it's going to go up to some extreme and down to some extreme, and it's going to be a y max and a y min, and it's going to go equidistant away from the equilibrium point. And I know it's not drawn to scale, but let's just assume that it is, that y min and y max are the same distance away from the dotted line. At the very, very top, we have a displacement that's at its maximum from the equilibrium, and it is changing directions. So if it's changing directions, that means that it is going to have a velocity of 0 because it's going from positive to negative. Then at the very bottom, it's going to do the same exact thing. It's going to go from negative to positive. So that means its velocity there is also 0. When we're at the equilibrium point, however, this is when we will have the maximum velocity. Because at that point, we have given all of the energy of the spring into kinetic energy. So we can also look at other things. So when it's at the top or the bottom, either one, I'm going to write it on the bottom. So when we are at the very, very bottom, we have all the energy of the spring. So the energy of the spring is at its maximum at that point because we have no kinetic energy at that point. And that means we would have all spring energy. Then when we get to the middle, the spring is no longer compressed or stretched, so the energy of the spring is 0, which means we have only kinetic energy. So we have all kinetic energy. Okay, so let's look at a sideways one instead, and let's actually put some numbers to it. So we've got a y max of 4 centimeters and a y min of minus 4 centimeters, and the period that it does this in is 0.7 seconds. So in that amount of time, it's going to go in one complete oscillation, or it's going to go 2 pi radians. So that means we can fill in the blanks of our equation here. So here we go. Here's the first part. So what would be the time it takes to reach the equilibrium point? So this is going to be a cosine. So that means at time 0, it already has some displacement, and that's going to be whatever the amplitude is. That's what this is right here. Oops. That's what that, why aren't you writing? There we go. That's what that A is. That's the amplitude. Amplitude. Okay, there's the amplitude. So, alright, let's erase that. So then we are going to try to find what that t is. So what is the time that it takes to go from that amplitude through the equilibrium point? So that means we can start filling in some of it. Our amplitude is 4 centimeters, and then we have the cosine of angular velocity times the time. So we need to figure out what this angular velocity is, then we can figure out how long it takes. But this is very easy to figure out, because regardless of what the amplitude is or what the object is, if it's in simple harmonic motion, then that means the period is completed in 2 pi radians, regardless of what it is. It doesn't matter what the amplitude is, it only matters that it went one complete oscillation, which is 2 pi radians. So the angular velocity is just going to be 2 pi radians divided by 0.7 seconds, and that's going to be 8.97 radians per second. So there's our equation for the position. Now, our question was, how long does it take to go from 4 centimeters to 0 centimeters? So what is t when y equals 0? So I'm going to rewrite this a little bit. So that means we have to solve this equation for t when y equals 0. Let's put it on the next page. So this is very easy to solve. If you remember some basic trig, if I divide both sides by 4, then I still have 0. 0 times cosine of 8.97 times t. Now, to get this t isolated, what we have to do is we have to get rid of this cosine. So to do that, you have to take the inverse cosine. And that means we take the inverse cosine of 0 on the left, and if we take the inverse cosine of cosine, it will cancel out. And so we'll just have 8.97t. Now, at this point, it's important to remember we are in radians on our calculator. So the inverse cosine of 0 degrees will give you something different than the inverse cosine of 0 radians. So we are going to use radians, and it will give us 1.57. Then we just have to solve the rest of this equation for t. So divide by 8.57, and bam, there's our answer. So it takes 0.175 seconds to go from 4 centimeters to 0. Okay. So this is where Physics 1 and Physics C will split in this video, because Physics C is now going to use calculus to answer this question. Physics 1, we are not going to be doing this because it involves taking derivatives. So Physics 1, you will tune in for part 2 for your video, and then Physics C, you will tune in for part 2 for your video.